program is to acquaint you with the physical and chemical properties of typical gas cargoes and their relationship to cargo handling requirements and safety aspects. The characteristics of liquefied gas can be broken into two main categories. Physical properties and chemical properties. For the purpose of this program, Part 1 will deal mainly with the physical properties and Part 2 with the chemical properties. This division, in practical terms, also generally separates itself into, firstly, characteristics affecting the liquefaction of gas cargo, and secondly, the integrity of the cargo and the surrounding environment. But let's now concentrate on gases and their physical properties. You'll remember that in Program 1 you were reminded that liquefaction depends upon pressure and temperature. In fact, certain gases cannot be liquefied by pressure alone. How liquefaction of a gas is achieved depends upon its critical temperature and its critical pressure. Critical temperature is the temperature at which a gas will not liquefy under pressure alone. This means, in practical terms, if the actual temperature of a gas is above its critical temperature, it must be cooled below this temperature before pressurization can turn the gas into a liquid. That is, allow liquefaction to take place. This table indicates the critical temperatures of the more common gas cargoes. It can be seen that methane has an extremely low critical temperature, and therefore considerable cooling is required before pressurization can achieve liquefaction. Critical pressure is the determined level below which liquefaction cannot occur. It's the balance between critical temperature and critical pressure which determines the liquefaction methods that can be employed for any particular gas, such as full pressurization, full refrigeration, or a combination of both as utilized in the semi-pressurized, semi-refrigerated ship. However, consideration must also be given to the other properties which we'll now discuss. Whatever method we use to liquefy our cargo, the gas and its surrounding environment will experience changes in temperature. In using fully refrigerated or semi-refrigerated techniques, we'll be deliberately causing the cargo temperature to change. It's therefore essential that we have a full understanding of the theory of heat transfer. The transfer of heat to or from a liquid gas gives rise to two significant physical changes: change in temperature and change of state from liquid to gas, or vice versa. These changes, of course, occur simultaneously. As heat is transferred to the liquid, the temperature rises. At a certain stage, that is, just prior to boiling, the temperature ceases to rise, though the liquid continues to absorb heat. A further stage is then reached at which the liquid boils or vaporizes, and the temperature of the gas vapor, now no longer a liquid, continues to rise. The heat that is absorbed by the liquid gas prior to boiling, without change of temperature, is known as hidden or latent heat. More specifically, it's known as the latent heat of vaporization. A similar phenomenon occurs in reverse during liquefaction. This time, latent heat is given up by the gas vapor just before it condenses to a liquid. Here are the latent heat values of some common cargoes. They are given in kilocalories. You'll notice that at the critical stage at which the gas changes its state, ammonia will need to lose or gain 3 times as much heat as the other gases. The speed at which a liquid can be evaporated or condensed will depend much upon the method of heat transfer. For instance, if a pot of water with its lid on is placed on a stove, it'll heat up until the lid lifts. Steam escapes and boiling water spills down the side of the pot. The whole body of the liquid is heated to the temperature at which it will vaporize. Capture of the vapor given off also accelerates this method of heat transfer. If the lid is completely removed at this point, the apparent level of boiling water will drop and the water will simmer. Why? Well, what has effectively happened is that when we removed the lid, the steam or vapor was allowed to escape, taking with it the latent heat it had absorbed. Prior to moving the lid, absorption of latent heat from the surface of the water had ceased. Thus, heat normally lost by the vaporization at the surface of the liquid was retained, and boiling was speeded up. The containment of vapour in this manner has direct relevance to the gas carrier. Let us, for instance, look at the dome of a cargo tank. Here we find vapour captured in the vapour space. Because this gas is in its vapour form, it will already have absorbed latent heat. If more heat, say from the sun shining on the dome, is absorbed by the vapour, it will now immediately be transferred to the liquid below. This in turn results in further vaporization. In the case of an LPG carrier, this is solved by recirculating the vapour through a refrigerator or reliquefaction plant. In the case of an LNG cargo, low temperatures prevent use of this method, and excess vapour, known as boil-off, is burnt by the ship's main boilers or vented to atmosphere. Gas will of course vaporize at different temperatures. We should therefore look at their boiling points, which you'll realize are affected by pressure. Increased pressure raises the boiling point. Conversely, reduced pressure lowers the boiling point. The relevance of this is that if the cargo is pressurized, its boiling point will be raised, and thus it will remain liquid at a higher temperature than otherwise. The semi-refrigerated ship makes use of this phenomenon. Here the cargo is semi-pressurized and thus can be allowed to reach a higher temperature than in a fully refrigerated and non-pressurized vessel. But now back to boiling point itself. Here are the boiling points of the more common cargoes given at the standard pressure of 1 bar. It's not always sufficient to think of the cargo in pure liquid or gas form. It must be remembered that during vaporization, vapor will carry varying degrees of moisture content. Excessive vaporization causes expansion and venting and increases the need for reliquefaction. Under certain conditions of temperature and pressure, a state of equilibrium will be reached, and such vapor will cease to vaporize to its full gaseous state. To carry our cargo successfully, we must reduce vaporization to a minimum, and thus the relationship between pressure and temperature is a critical factor. Just to recap, it's the combination of these factors which maintains the equilibrium of the cargo. The three factors are: 1, the gas itself; 2, the pressure at which it's carried. Increased pressure reduces vaporization. And 3, the temperature at which it's carried. Reduced temperature reduces vaporization. The suitability of a ship to carry a particular cargo will depend, of course, upon the refrigeration and pressurization plant